So inductors, yes. No, half power means half power. It's 0.707 in voltage. But, okay. We're going to deal with inductors, but not really as explicit components that we will put into the circuit. But all the motors and solenoids that we're going to deal with have coils of wire in them that make them behave like inductors. So it's important that we're aware of that behavior. And it is, the behavior is that the inductor resists changes in current through it. And it responds by creating a voltage drop in order to resist those changes in current. So when I first close this, it's much like a paddle wheel with inertia. As soon as I open the valve, the paddle wheel doesn't start spinning right away. It slowly spins up as the current, or as the flow through it builds. And then if I suddenly close the valve, it doesn't stop instantaneously. It keeps spinning, creating a high pressure downstream and a low pressure upstream. So it creates a pressure potential across it, just like the inductor will create a voltage across it in response to changing currents. The unit is the Henry. We are typically dealing in the micro to millihenry range for the kind of inductors that we're likely to encounter. The symbols are just curly lines. The unit, or the characteristic equation is L di dt, where L is the amount of inductance. And we said that where capacitor responds to changes in voltage, an inductor responds to changes in current. The inductor is also an energy storage device, much like the capacitor, only now it's in terms of current. That current flowing through the device builds a magnetic field, and that magnetic field is storing energy. When we try and stop that flow of current, that magnetic field collapses, and that's got to go somewhere. I'll skip those. So here's the situation that you're likely to run into in more than one instance, where you've got an inductor, you close the switch, you turn the motor on, you energize the solenoid, it's done its thing, and you're trying now to make it stop, so you want to open the switch. What's going to happen to V when you open the switch? It will go to infinity. Yes, in the ideal sense, I mean, if we could do it, if we could actually instantly open that switch, we would create an infinite dIdt, and we would see an infinite voltage drop, or a voltage differential created across the device. The reality is that when you open that, if you open it very quickly, you'll get a very large dIdt. That will create a very large voltage, which will actually arc across the contacts of the switch and allow some current to flow and allow the dIdt to come down to something that really, that's more physically possible. This is going to become an issue because these voltages that it jumps up to are very easily hundreds of volts. And they can destroy semiconductor switches. They wear out mechanical switches. They can destroy semiconductor switches in just a matter of seconds. Okay? So the key thing to be aware of is this spike in voltage that happens whenever you try and turn the current off. And when we come back on Tuesday and start talking about semiconductors, I'll show you how you can use a semiconductor to tame that spike of voltage. All right.